Hi guys, David here with another science update. So today I want to talk about a paper called Research Reveals Potential of an Overlooked Climate Change Solution. So they say earlier this month, President Biden urged other countries to join the US and European Union in a commitment to slashing methane emissions. Two new Stanford-led studies could help pave the way by laying out a blueprint for coordinating research on methane removal technologies and modeling how the approach could have an outsized effect on reducing future peak temperatures. So methane, like carbon dioxide, is considered a greenhouse gas. It's a little bit different. Methane is CH4, whereas carbon dioxide is CO2. And they have one of the differences about them is that methane is a much more potent greenhouse gas compared to CO2. Carbon dioxide, or CO2, gets a lot more attention, partially because it's much higher in concentration in the atmosphere. So the concentration of CO2, according to a quick Google search, is about 410 parts per million, whereas the concentration of methane in the atmosphere is about 1.8 parts per billion. Or in other words, it's about 1.8 parts per million. So we're talking about 1.8 parts per million for methane versus about 410 parts per million for CO2. So there's much more CO2 in the atmosphere than methane, but methane is considered a much more potent greenhouse gas. So if you multiply this 1.8 times 81, you're getting in the range of probably about 150. It's like 150 parts per million versus 410 parts per million if you're really looking, really comparing them apples to apples in terms of their greenhouse gas warming effect. So methane, even though it's much lower in concentration, we can't really ignore it. The article goes on to say that under a high emissions scenario, a scenario in which the human race continues to emit a lot of greenhouse gases, their analysis showed that a 40% reduction in global methane emissions by 2050 would lead to a temperature reduction of approximately 0.4 degrees Celsius by 2050. And I believe in the high emissions scenario, the idea is that the global temperature will probably rise about 2 degrees centigrade by 2050. So 0.4 degrees, if you could reduce 0.4 degrees of that, that's about a 20% reduction from the peak. So that points out that if you could remove more methane from the atmosphere, it would probably have a pretty potent effect on global warming overall. But they say that methane is challenging to capture from air because its concentration is so low. But burgeoning technologies such as a class of crystalline materials called zeolites capable of soaking up the gas hold the promise of a solution, according to the researchers. They argue for increased research into these technologies' cost, efficiency, scaling, and energy requirements, potential social barriers to deployment, co-benefits, and possible negative byproducts. And I should mention that even if they don't disclose it, researchers like this essentially have a conflict of interest. So it's interesting, these guys are, or people are at Stanford University, and they are dependent on grant funds. And so it's interesting, or not surprising, that the conclusion of their paper, their treatment of the subject, says that what we need is more grant funding. That will solve everything. So I have to poke fun at that a little bit. But it is an interesting point of view overall. And it got me into looking at CO2 capture. There are companies right now that are actually building out factories, I guess you could call them factories, facilities for removing CO2 from the air. So this is one. Climeworks is based in Iceland, I believe. And you can see their design. They have these boxes with fans. And so they say our machines consist of modular CO2 collectors that can be stacked to build machines of any size. So the way that their collector boxes work is they have a fan and it blows CO2 into a membrane that collects it, a highly selective filter material that sits inside the collectors, and then the rest of the air can leave. After the filter material is full with carbon dioxide, the collector is closed, and we increase the temperature to between 80 and 100 degrees C, which releases the carbon dioxide. Finally, we can collect this high purity, high concentration carbon dioxide. However, there's a lot of energy cost here. First of all, they need energy to run the fan, and that's not insignificant because they're running a fan but through a filter. So that's going to take a lot of energy to run that fan. And then second, they need to close these boxes and then heat the material to about 100 degrees C, which is more energy. So it looks like it takes a lot of energy to run this CO2 capture. And remember, the thing about energy is that most of the time energy is associated with carbon dioxide release. And they say that they get their energy from either renewable energy, and I think since it's in Iceland, there's probably geothermal involved, so that's very, very clean energy. But they also get it from burning trash. And burning trash, well, I mean, that's a legitimate thing to do. I support burning trash especially plastics, rather than letting them just stay environmentally persistent. It definitely releases a lot of CO2. So this kind of thing it's interesting, and I'm glad that people are doing experiments with it. But it really only works if you have vast amounts of renewable energy. And for that, I would think, or clean energy. And for that, I would think you would need probably nuclear fission or ideally nuclear fusion to be online to a great degree. So in about 50 years, I think this kind of thing will be a lot more viable, but by then it might be too late to avert major atmospheric change. What's interesting is if you think about this in terms of methane, perhaps if you were doing something like this with methane, the difference would be instead of having a CO2 filter inside the box, you would have some zeolite type material which would selectively hold on to the methane. Maybe after you were done, you could burn the methane. And I know you would release CO2, but if methane is actually 81 times more potent than carbon dioxide in terms of a greenhouse gas, that's really still a win, because the molar ratios, or the atomic ratio, if you burn one CO2, one methane, you're gonna yield one CO2 and quite a bit of energy. They could then take that energy and use it for the heating processes that they need, and maybe even convert some of it to electricity to run their fans. That could be a viable process. So hopefully someone can think of a way to get that done, or test it to see if it's viable. But overall, this article was interesting because it gave me a chance to look at even though methane is so much more dilute in the atmosphere, by the time you factor in the fact that it is really a very potent greenhouse gas, you can't really ignore the role of methane in climate change. And hopefully we can find ways to reduce it, or maybe capture it without severely affecting our day-to-day lives. One of the things that has been pointed out is that when you look at the global methane production, a lot of it is actually made from agriculture. So some of it comes from fossil fuels, but a lot of it's from agriculture, and then a lot of it just comes from wetlands, just naturally. So that's the thing is I really don't like to hear about people's plans to change the way that people are eating. That seems pretty dystopian, especially if they want us to eat highly processed meat substitutes, and that's the future. As a synthetic chemist, I have a good understanding of what goes into meat substitutes, and I don't really want to eat them. I think that meat is healthier. I think instead we should be looking at perhaps reducing the fossil fuel production of methane, and maybe looking into ways to capture methane. That would be cool. The other article that I want to talk about today is from Scientific American, and it's called How to Search for Life as We Don't Know It. And I've linked it below. I think it's a really interesting thought piece by Avi Loeb. And he's talking about essentially that when we're picturing what extraterrestrial life will be like, we're primarily thinking of it in terms of what we've known life to be like. We know life in our context is heavily dependent on water, for instance. And there's just even design motifs that are prevalent in our minds that may not actually be we'll say like the be-all, end-all of what it is to be life. So he says, when trying to imagine something we've never seen, we often default to something we have seen. For that reason, in our search for extraterrestrial life, we are usually looking for life as we know it. But is there a path for expanding our imagination to life as we don't know it? He says the adaptation of life to extreme environments could take exotic forms, as exemplified by extremophiles on Earth. For example, frozen microscopic animals were recently discovered to survive 24,000 years in the Siberian permafrost, and microbial life was found to persist 100 million years beneath the seafloor. Anyway, I encourage you to check out the article, it's a good read. Well, this has been another Science Update. Thanks so much for watching. Hope you'll join me again in the future soon. Bye.